Okay, this is exam 3 for physics 102. Which of these statements about a household circuit is true? A GFCI turns off if IN is greater than I out. That is a true statement. Devices in a house operate all at the same voltage. That's true. As you add more devices, the total current increases because they're in parallel. As you add resistors, the total current does increase. And the current to a device in a household circuit will decrease if other devices are removed. That would be true if they were in series. Actually, the current would increase if other devices are removed in series, but a household is laid out in parallel. So only 1, 2, and 3 are correct. On a circuit breaker, you have these devices, and then you add a blender, and the circuit breaker turns off. What is the maximum allowed current? So we've done these before, but let's go through them. First of all, I want to find the current for each. I is equal to P over V. So for the 2400 watts divided by 120 volts, that's equal to 20 amps. So I have 20. Here I have 1 amp. Here I have a half an amp. So when it's operating, I have 21.5 amps on this circuit breaker. And then I add 4 amps, which is 25.5 amps. So somewhere between 21.5 and 25.5 is where my circuit breaker kicks off, because the circuit breaker turns off when the current exceeds a certain amount. And so the only one in between those two is 25 amps. Okay, which of these equations is correct? 3 minus 2I1, I'm starting up here, minus 2I1, so far correct, plus 5, minus 6I1. Two problems with that. That minus 6I1, it should be I2, and it should be positive 6I2. So that's not correct. Let's see, 5 minus 6I2. That would be 5 minus 6I2. Okay, that's not correct. It should be plus 6I2. Then keep going. It is minus 6. So that one's not right, nor is B. Minus 6 plus 2I1. I'm going in this direction because it's minus 6. Plus 2I1. That's correct because I'm going against the current, and the current is I1. And then minus 3, that's correct because I'm going from high to low potential. So that is the right answer, C. Now, if I2 is 0.17 amps to the left, what is the magnitude of I3? Well, see, a couple ways I could do this. Let's clean this up a little bit. The easiest way is to take the junction rule. So if I take my junction rule right here, my junction rule is I1 plus I2 is equal to I3. I want to know I3. I've been given I2, and so I want to find I1. But look, I already have the equation to find I1, so let's just use that. I get 2I1 equals 9, so I1 equals 4.5. Yeah, and so now if I want to know I3, well, I1 is 4.5, I2 is 0.17, that's equal to I3, so it's going to be 4.67 amps. That's C for number 4. Now, what is the current through the 3 ohm resistor? Well, there are no currents listed here, so I just need to label some. I'm going to call this I1, I'll call this I2, and I'll call this I3. And through the 3 ohm resistor, that's I1. So I want to know what I1 is. I want to pick a loop. I'm going to use this loop because there are no resistors on that right-hand side. It makes the math a lot easier. Let's go start here and go in this direction. So that's going to be 4 minus 3I1 minus 12 equals to 0. There are more complicated ways that you could do this, but this is the simplest. It's negative 3I1 equals 8. So I1 is negative 8/3. Oh gosh, what is 8/3? I think that's 2.7. Yeah, 5 is D, 2.7. And notice that if I'd asked for a direction, the direction of I1, I had listed it as being to the right, but really I1 flows to the left because it came out negative, but I didn't ask that. Consider a series charging RC circuit for which R is 2 and C is 10. The capacitor initially has no charge, and then I hook up a battery. What is the charge after 5 seconds? So, for a charging capacitor, Q is equal to Q naught, that's C over V, or C times V rather, times 1 minus e to the minus t over RC. For a charging capacitor, the function looks like this. It's an exponential growth function, Q versus T. Q naught is equal to C times V, so that is 100 microcoulombs times 1 minus e to the minus t, which is 5 seconds, and then over RC, and tau is equal to RC, which is going to be 2 megohms times 10 microfarads. Notice the mega and the micro, they both cancel out, so that's going to be 20 seconds, so it's 5 over 20 seconds. And then that'll give me my answer. It's going to be 20 microcoulombs for number 6. Just double check that. Make sure that you can do these calculations in your calculator. So this is equal to 100 times 1 minus 0.77. Yeah, so it's 23, rounded off to 20. Okay, which of these is the charge versus time for a charging capacitor? I already said it's going to be that one, B. After 3 time constants, what percentage of a final voltage EMF is on an initially uncharged capacitor charged through a resistance R? I'm sorry, let me pause for just a moment. Okay, sorry about that. So this is from an OpenStax question. After 3 time constants, what percentage of a charge is on an initially uncharged capacitor, of the final voltage rather. So this is a charging capacitor, and on a charging capacitor, V is equal to V naught times 1 minus e to the minus t over RC. And I want to know what is the percentage. That is, what is V over V naught? And so that's going to be equal to 1 minus e to the minus. And here I'm looking for 3 time constants. So that means that t is equal to 3 times tau. So I'm looking at 3 tau divided by tau, or just e to the minus 3. And this is equal to 0.95. That's equal to V over V naught. So I'm looking at 95% of my voltage, so that I'm at 95% of my maximum voltage. So the answer is C for number 8. All right. Consider a thin wire bent into the shape of a ring, carries a steady 2 amp current. The value of the magnetic field is what? Okay, so this is going to be our B is equal to, well, let's look at that equation sheet. I'll pause while I pull it up. The equation sheet has the magnetic field due to a coil of wire. That's going to be this B equal N mu naught I over 2R. I know that because it has the N in it, and that's related to a solenoid. I'm not looking at a long straight wire, although I am looking at just a single wire, so N is equal to 1. So this is going to be 4 pi times 10 to the minus 7. I is 2 amps, and 2 times R, which is going to be 0.1 meters. It's 10 centimeters. Let's see, the 2 cancels there, and so I'm left with 4 pi times 10 to the minus 7 over 0.1. I get 1.3 times 10 to the minus 5th Tesla, That is 13 times 10 to the minus 6 Tesla, or 13 microtesla. So C for number 9 is right. Electron, by the way, this was an OpenStax question. Electron is moving at 3 times 10 to the 5th in positive x direction. What is the magnetic force? A magnetic field of 0.8 teslas in the positive z direction. What's the magnetic force? Hey, let's first just look for the direction of the magnetic force. So my speed is in the positive x direction, that's v, my velocity rather. My magnetic field is in the positive z direction, so that's b. Let's do our right-hand rule. V is to the right, B is out of the page. That means that the force is going to be down, that it's in the negative y direction. Oh look, we can pick the answer here. That has to be E because that's the only one with negative y direction. Let's go ahead and find out the magnetic force. It's equal to QVB sine of theta. Theta here is 90 degrees, so I'll just leave that off. Q is 1.6 times 10 to the minus 19. V is 3 times 10 to the 5th meters per second, and B is 0.8 Tesla. And if I do that, I get 4 times 10 to the minus 14 newtons. So it is E. How far from a straight wire carrying 0.45 amps is the magnetic field strength? 0.040 Tesla. Where our magnetic field, if I go back to my equation sheet, is going to be this mu naught I over 2 pi r. B is equal to mu naught I over 2 pi r. And I'm looking here for r. I'm looking for the distance from that wire. Mu naught I over 2 pi b. And now I put in my values. 4 pi times 10 to the minus 7. I have 0.45 amps divided by 2 pi, and b is 0.04 Tesla. The pi's cancel. I get rid of that 2. So I'm looking at 0.9 times 10 to the minus 7 divided by 0.04. 2.25 times 10 to the minus 6. That's 2.3 micrometers. So number 11 is C. Which creates a magnetic field. By the way, that was a concept test. Moving charges create a magnetic field. A magnetic field cannot do which of these? It does exert a force on a moving charge. It does change the direction of a charge's motion. And because it changes the direction, it can also change the momentum. Remember, momentum is a vector quantity. So if I change the direction of a quantity, it changes the actual quantity. But it does not change the kinetic energy. That's an important idea. When we look at a mass spectrometer, it only changes the direction of the velocity. It doesn't change the magnitude of the velocity. In order to change the kinetic energy, you have to change the magnitude of the velocity. You have to change the speed, and it does not do that. Positive charges traveling towards a wire is shown. The charge follows a path is shown. What is the direction of the current in the wire? So first of all, we need to figure out what is the magnetic field that causes this motion. Well, it initially feels a force in this direction, and it has a velocity in this direction. And that force causes it to swerve off to the left like this. So what magnetic field has caused that? Well, looks like a magnetic field that is out of the page on this side of the wire has caused a force in that direction. That means it's going to be into the page on this side. Now we use our third application of the right-hand rule to figure out what is the direction of that, and I get to the right. So I have to have a current to the right. So 14 is B. Positive particle travels as shown through the magnetic field. In order to go undeflected, an electric field must also be present. What is the direction of that electric field? Okay, first of all, it's a positive particle, so let's figure out what is the direction of the magnetic force. The magnetic force is going to be up. That means that my electric force has to be down. That means that my electric field, because this is a positive particle, is also going to be down. So number 15 is B. Proton travels in the minus x, magnetic field in the plus y. The direction of the force acting is what? So proton travels with a speed in the negative x. The magnetic field is in the positive y. So I get that the force is into the page. That's the negative z direction. So number 16 is D. I think that was an OpenStax. These are the types of light in electromagnetic spectrum listed alphabetically. Arrange them in order from lowest to highest energy. Okay, of these four, the lowest energy is infrared, so that gets rid of these three. And then next is visible. Then next is X-ray, that gets rid of this one. And then gamma ray is the highest energy. Which of these statements are true? Newton believed light was a particle because of reflection. Huygens believed light was a wave because of refraction. He did believe light was a wave. Einstein showed light, or he believed light was a particle because of the photoelectric effect. And Young showed light was, he thought it was a wave because of interference. So all of these are wrong for various reasons. None of these are true. Okay, I have two mirrors at 90 degrees. I have an incident ray at 60 degrees. What is the angle of the reflection for the second ray? This angle is 60. That means this angle is 30. 30 plus 90 is 120, so that means this angle has to be 60. This is 30, and so this is 30 as well. So the angle is 30. Notice, by the way, this is a pretty good drawing, so you can tell that these two rays are parallel to one another. That when you have a light ray incident on a right mirror, two right-angled mirror, or two mirrors situated with a right angle, they will come back parallel to one another. Light travels through three media, as shown here, which has the highest index of refraction. Okay, so here it slows down so that this can travel around. That means that N2 is bigger than N1. Here, it speeds up so it travels in that direction. That means that N2 is bigger than N3. Oh, well, we can just stop right there. It doesn't even matter the relationship between N1 and N3, because I know that N2 is bigger than both of them. So B is the right answer for number 20. Light travels from glass to the air. The index of refraction is 1.5. Incident angle is 30. What is the refracted angle? So I'm going from glass to air. I have this angle is 30 degrees, and I want to know what is the refracted angle. First of all, is it going to bend towards or away from the normal? When it comes into the air, this part will speed up, so it's going to bend in this direction. So I know this angle better be bigger than 30 degrees, and so I can get rid of C and E. So it's going to be AB or D. So I have 1.5 sine of 30 equals 1 sine of theta, and I solve that for theta. It's the inverse sine of 0.75, which is 49 degrees. A is 21. Components of some computers communicate with each other through optical fibers, have an index of refraction of n equal 1.5. What time in nanoseconds is required for a signal to travel through 0.6 meters? First, I need to find the speed of light in that. That's going to be c divided by n, 3 times 10 to the 8th meters per second, divided by 1.5. That's going to be 2 times 10 to the 8th meters per second. Then I want to figure out how long does it take. Well, time is equal to d divided by v. If you don't believe me, look at our units. That's meters over meters per second. That's equal to seconds. That's going to be 0.6 meters divided by 2 times 10 to the 8th. That's 3 times 10 to the minus 9, or 3 nanoseconds. So B is right for 22. Optical fiber uses two transparent materials. The core is in the middle of the fiber, and then the cladding covers the core. So I have a core like this, and then I have another material, the cladding, that surrounds it. This is the core. And I want to know which of these will serve as the cladding. Remember, this has to be low N, and this has to be high N. So the one with the lowest value for N, which is the crown glass, will be the cladding. I don't think that crown glass would make a very good cladding. I don't know if it's the appropriate material, but at least as far as the index of refraction, it would be okay. The next one's a follow-up. What is the critical angle? So if I'm going from, what were my indices? From 1.66 to 1.52, as my light ray is traveling from n equal 1.66 to n equal 1.52, my critical angle is going to be this angle that will give a refracted angle of 90 degrees. So it's going to be n1 sine theta 1, that's 1.66 sine of theta c, equals 1.52 sine of 90. This, of course, becomes 1, and then my critical angle is the inverse sine of 1.52 over 1.66. I get 66.3 degrees, so B is the right answer for 24. You stand 2 meters in front of a flat mirror. Which of these correctly give the image distance and magnification? Oh, A is the right answer here. Your image distance is the negative of your object distance, and your magnification for a flat mirror is always positive 1. An image has a magnification of +2. Which of these statements is correct for this image? Okay, 1 is correct, so that gets rid of that one and that one. The image is virtual. Maybe, let's come back to that. The image is upright. That's true because this means that it's upright. So, and the image is inverted. Not inverted because it's positive, so it gets rid of that. So what about number 2? Is the image virtual? Let me remind you, magnification is negative Q divided by P. In order for this to be positive, this has to be negative. Our object distance will always be positive, at least in one lens system, one lens or one mirror system. So P is always positive, except for some special cases, which we'll see later. So if Q is negative, for magnification to be positive, then the image is also virtual. So A is the right answer for 26. There's this diagram, which ray is drawn incorrectly? Well, all of these are correct. And we can tell by a couple of ways. One, we can look and see the incident and reflected angles. They're all equal. These angles are equal to one another. Another key is that they all cross, the virtual rays all cross at a position where my image should be, that it should be exactly opposite where the object is. So all of these are correct. Flat mirror produces an image that is, well, virtual, so I get rid of these two, upright, so I get rid of that one, and same size as the object. So A is the right answer for 28.